Assalamu alaikum. My name is Mohammad Farzam, and today we'll be solving the Cambridge AS level chemistry paper, which is theory paper variant 2 and from February March 2026. So let's get started. Alright, so if we move on, the first question says that the group of two elements, magnesium to barium, where they show strengths in their physical properties down the group. Right, so we have some values, some properties of these elements, right, of the group 2 elements. So we have the electronic configuration, their proton number, the sum of first and second ionization energies, and the third ionization energy. So first it says to give us the final or the full electronic configuration of a calcium atom, right? So for calcium has 20 protons, right? If you see here, calcium has 20 protons, so the electronic configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this would be the full electronic configuration for a calcium atom. Now in part 2 it says to explain the trend shown in the sum of the first and second ionization energies as proton number increases. So we need to explain the trend that why the sum of the first and second ionization energies decreases as we move down. So as you can see, as you move down, the electrons are removed from a new shell. The valence electrons are in the second shell, in the third shell for magnesium, then they are in the fourth shell for the calcium, and then it increases. Right? You can look at the periodic table for that. Your calcium is the calcium is in the fourth period, right, and magnesium is in the third period. So the valence electrons, or the electron to be removed, are from a new shell. So what happens, the electron is removed from a new shell, so this increases the distance from the nucleus as well as the shielding effect. That's why the second ionization energy increases. That's why their sum also increases, right? So the electrons are removed from a new shell, from a new shell as we move down the group, as we move down the group. This increases the distance from the nucleus. This increases the distance from the nucleus and the shielding electrons. Distance from the nucleus and the shielding electrons. Right. So this is the explanation for this string. Then in part 3 it says write an equation to represent the third ionization energy of barium. Right, so we need to represent the third ionization energy of barium. So for barium, this is because the third ionization means that we are removing this third electron. So third electron is removed from a gaseous ion of +2, right? So the equation would be barium +2, right, with the state of gaseous state, right, and we will be removing an electron, so we will be getting a barium +3 ion, which will also be gaseous, and one electron, that would be E negative. So this shows that the electron is getting removed from the barium +2 and it is becoming a barium +3. So this is the third ionization energy, removal of the third electron. Then it says explain why the third ionization energy of magnesium is much higher than the sum of its first and second ionization energies. The reason for this is magnesium has two valence electrons. All of these, they belong to group 2, so they all have two valence electrons, right? So when two electrons, the first two electrons are removed, that is first and second ionization energies, right? The valence shell is there are no electrons in the valence shell, so now the electrons will be removed from an inner shell. So due to that, your distance from the nucleus decreases, your shielding decreases, because the electron is now removed from an inside shell, right? So due to that, the third ionization energy is far much greater than your second and first summed, right? So why the third ionization energy? Because magnesium has two valence electrons, right? Electrons, and the third electron is removed from an inner shell, is removed from the inner shell, from the inner shell, which has greater electrostatic or a greater nuclear charge and lower shielding. That's why the third ionization energy will be greater than the two summed, right? And then in the next part B, it says that strontium reacts with water, an alkaline solution is produced. Write an equation for this reaction. So when strontium reacts with water, right, it will form a strontium hydroxide, which will be strontium OH2, and we will have hydrogen gas, which will evolve, right? So now let's just label the symbols here. So strontium will be a solid when we will, because it is a metal, alkaline, but these are group 1 and group 2 are soft metals, so that would be a solid. At this point, water will be liquid, right? And this would be an aqueous solution, right? Because this is soluble in water, and hydrogen will be of gas. And now to balance it, we would need to just add 2 here to make it balance, right? 2 moles of water molecule, and this would be balanced. Then it says separate samples of alkaline solution, which is a strontium hydroxide. They are tested with dilute HCl and separately with dilute sulfuric acid. So what would you observe in each of these? So what will happen? This is alkaline, this is an alkali, right? Alkali, we have two acids, the dilute sulfuric acid and dilute HCl. So we will get strontium chloride, and the products would be strontium chloride and water, because this is acid plus alkali reaction, which gives us salt and water. And over here it would be strontium sulfate and water, right? So because strontium chloride is soluble, it is a soluble salt, we would not see anything here. So no reaction or no observation, you can write no visible observation. But in this case, the salt produced, which is strontium sulfate, is insoluble because the solubility of sulfates decreases down the group, right? So it would be white precipitate. We will see white precipitate, you can write it as white PPT, right? So yeah. Then it says in part C that the nitrates and carbonates of group 2 elements decomposes on heating, illustrate the trend in the thermal stability of the group 2 carbonates down the group. So the trend is that the thermal stability increases. And then for the second part, it says write an equation for the thermal decomposition of calcium nitrate. So I would suggest that you should remember this equation, learn this equation. It could be asked for any group 2 nitrate or carbonate, right? So you should know the thermal decomposition equations for nitrate also and carbonate also. Well, it is very easy to it is very easy if you just remember the products also. It is very easy to balance out, right? So however, the products are calcium oxide plus nitrogen dioxide and oxygen, right? So we will have 2 here, right? Then we will also have 2 here, we will have 4 here, and this equation is perfectly balanced. Then it says that the calcium chloride, which is used in water purification, in the same way as sodium chloride. So calcium chloride can be prepared by the reaction of aqueous calcium hydroxide with chlorine. Write an equation for the reaction of cold dilute OH negative ions with Cl2. So this is the same reaction that you would have learned for NaOH, cold NaOH. So instead of NaOH, you have calcium hydroxide. This is the only difference, right? So the ionic equation would be same as of your chloride equation, NaOH equation, but the only difference would be of twice here, because we have twice the hydroxide ions than if you compare it with sodium hydroxide ion. So that would be 2 times sodium hydroxide will react with chloride ions, right, to give us ClO, which is the chlorate ion, right, the chloride ion and the water. So this would be the equation. Think this way there, it would be chlorine Cl2, my bad. Yeah. So we have the chlorine gas here. All right. Then state why NaClO and calcium CaClO2, which is sodium chloride and calcium chloride, why they are used in water purification to kill bacteria or to kill microbes, right? You can write either. So now we are done with question 1. Let's move on to question number 2. So in question number 2, it starts with that we have a nitrogen monoxide, which is an atmospheric pollutant. We have a dot and grass diagram for the nitrogen monoxide. So it says NO has an unpaired electron. State the term for a molecule with an unpaired electron. So that is a free radical, right? With something, any species which have an unpaired electron is basically a free radical. Now it says in NO, the N and O atoms are bonded by a sigma and a pi bond. So we already have a sigma bond, which is being shown by this line. we need to make the pi bond. So pi bond is basically made up and down like this. So this is your pi bond, right? This whole makes up the pi bond, right? Now in part B it says that in the laboratory nitrogen monoxide is made in the reaction of copper metal with dilute nitric acid. The reaction is kept cold to prevent the oxidation of NO, right? So we have the nitric acid reacting with copper, and with this reaction we are getting copper nitrate as well as water and nitrogen monoxide. So we have the moles of copper which reacts with excess HNO3, and the temperature is at 5 degrees centigrade, and the temperature and the pressure is atmospheric pressure, which is 101 kilopascals. So we need to figure out the maximum volume in centimeter cube of NO that is produced under these conditions. So first we will be applying, because we are at standard conditions, we can apply the ideal gas equation, which is PV equals nRT, right? For this we need to know the pressure, volume, we need to find the volume. To find the volume we must know the pressure, the R, which is constant, which is 8.314. We must know the temperature and the moles. So we already know the pressure and the temperature. The only thing that we need to find out is the number of moles of these gas produced, right? So we already know the moles of copper, which is 0.00393 moles, right? And we know the stoichiometric ratio between copper and nitrogen monoxide. So the stoichiometric ratio says that 3 moles of copper gives us 2 moles of NO. So if I have 0.00393 moles of copper, how many moles of NO would I need, right? So this moles of NO would be equals to 0.00393 times 2 divided by 3. Now if I use the calculator for this, so I will get an answer for the moles of NO that would be 0.00262, right? So these are the moles of nitrogen monoxide. Now using the ideal gas equation, I will now find out the volume, right? So pressure is 101 kilopascals, right? So you can use 101 multiply by 10 to the power 3, because the unit should be in pascals. This is kilopascals. We need to find the volume, right? Moles are 0.00262, right? And I'll just shift this everything a bit here so that I get space. All right, yeah, 0.00262 is my moles, right? It is 8.314, and the temperature would be 278, because we need to put it in Kelvin. So volume would be equals to 0.00262 multiplied by 8.314 multiplied by 278 divided by 101 multiplied by 10 to the power 3, right? Now because the answer would be in decimeter cube, we need the answer, it would be in meter cube, we need the answer in centimeter cube, right? So do that, we would be multiplying with 10 to the power 6. 10 to the power 6. This is the conversion unit, right? So the final answer that we would get for our volume would be 59.9 centimeter cube, right? So calculate this all out, put this whole expression in the calculator, and you will get 59.9. Then in part C it says state a natural process that creates atmospheric NO. So that would be lightning activity. Whenever we have lightning activity, the lightning provides the high activation energy to break the bond between nitrogen molecule, which is a triple bond, and then nitrogen reacts with the oxygen, which is in the atmosphere. Then it says photochemical smoke forms when NO reacts with unburned hydrocarbons. Identify the major component of photochemical smoke, right? So the major component of photochemical smoke is PAN, which is peroxyacetyl nitrate. Then we have NO, which is a catalyst. It says that the nitrogen monoxide has a catalytic role in the oxidation of atmospheric SO2, right? It is catalyzing the oxidation of sulfur dioxide to sulfur trioxide. So we need to show relevant equations which show this catalytic role. Now, how to show this catalytic role is the catalyst is unused in the reaction, which means it will be used up during the reaction and will be reformed at the end of it, right? So let's start. So we have SO2 which reacts with O2 to give us NO3, SO3, right? So what will happen now? This first, your NO will react with half moles of O2 to make it NO2, and then this NO2 will react with SO2 in the oxygen to give us SO3 and NO. So in the end, the nitrogen monoxide is reformed again. So this shows the catalytic role, right? All right. Then it says in reaction 1 occurs during the catalytic removal of NO from car exhaust gases, right? So we have one reaction which is occurring in the car exhaust. So we have the activation energy, right, of this reaction is 570 kilojoules per mole. We know the enthalpy change also. We need to complete this energy profile diagram. So first, because this is an exothermic reaction, right, the reactions are the energy of the reactants and the energy of the products. You should know the difference. If it is an exothermic reaction, the energy of the products would be less, right? But the activation energy is the energy from the energy of the reactants to the higher most energy. So this means that the arrow that we will make up for the activation energy would be higher in length, right, than the arrow that you will have for the enthalpy change, and opposite in direction. So you need to make sure of these two things, right? So when I will make this hump, right, so I'll just label the two things first. This is my activation energy and this would be my enthalpy change in comparison to my activation energy. So now I will draw my first, let's draw the uh, products, right? Let's label it. This is half N2 plus C, and now let's make the diagram. So this will be something like this. It will go up, yeah, with a hump, and then it will come down. So this would be the the energy profile diagram. Just remove the arrows, right? It is just to show that the activation energy is greater than your enthalpy change and opposite in direction also, right? You should, because you know the values, this should reflect in your energy profile diagram, right? And now we need to label it also, yeah, show the enthalpy change and the activation energy. So yeah, just label it. This would be your activation energy right here, EA, and this would be your enthalpy change, delta H. Right. Then it says on your diagram, show the addition of a catalyst. How does the catalyst affects reaction 1? So the catalyst only lowers your activation energy, right? So you would show it like this. You can use a dotted profile for it, right? Like this, that the activation energy drops. Everything remains the same. Nothing changes. The enthalpy change doesn't changes, only the activation energy changes. So you can show a dotted line, a dotted graph to just show that your activation energy drops. Okay, then let's start with question 3. Question 3 starts with, we have a secondary halogen alkane, which are important building blocks in organic chemistry. So we have 2-chlorobutane, which is an example of this secondary haloalkane. So it says explain why 2-chlorobutane is classified as a secondary halogen alkane, because it has, you can say it has two radical or the two methyl groups attached, right? One here and the one here. Or you can also say that it has only one hydrogen attached to it, right? That the carbon has only one hydrogen attached to it. So you can say both means the same thing. You can say that the carbon has only one hydrogen attached to it, or the carbon has two other carbon atoms attached to it. Both would be correct, right? So the carbon chlorine, the carbon with the chlorine, the carbon with with the halogen, has two other carbon atoms attached to it. Has two other carbon atoms attached to it. Right. Then in part B, it says that the 2-chlorobutane can be formed by the electrophilic addition of HCl to different isomers of C4H8. Compound A is one of these isomers. So if you go with the electrophilic addition of HCl, right, 2-chlorobutane, how can we form 2-chlorobutane? If we do electrophilic addition on C4H8, right? So one of these isomer is C4H of C4H8 is this. We need to draw a structural isomer of A, that is C4H8, that can also form 2-chlorobutane when it reacts with HCl, right? So if you see, this would be this could be something like this, that if I have 2 here, 1 2 3 4, right? So we have, this one is, if you look at it, this would be 1 2 3 4. So this is butene, right? So but1ene would also give us 2-chlorobutane, because the chlorine would be attached here, right? So it could be butene also. So this would be my isomer in this case. Then it says draw and give the systematic name of the geometrical isomer of A. So A is basically the cis one, right? So we need to make the trans for it. So trans would be like this. This would be the trans. You can show the double bond here, and the systematic name would be trans butene. Butene. So this is the geometrical isomer of your A, right? Then okay. Then in part 3, it says and explain the origin of geometrical isomerism in alkenes. So what happens is this double bond restricts the rotation, individual rotation, right? What does the double bond does? It restricts the individual rotation. So when it will rotate, they will rotate as a pair. They will rotate as a group. It will move down and this will move up, right? So the double bond restrict the individual rotation of the compounds, right? That's why we get these isomer, that is the geometric isomers, right? So we'll just start with this. So the carbon to carbon double bond restricts the individual rotation, of the group of atoms attached which are different for each carbon, right? Which are different for each carbon. Right now, the last statement that I said, which are different for each carbon, this means that the two atoms which will be attached with one carbon on the double bond and the two atoms which will be attached to the other carbon on the double bond, they should be different from each other, right? Yeah. Then in part C, it says butane C4H10 reacts with Cl2 in the presence of ultraviolet light to form 2-chlorobutane, which has molecular formula C4H9Cl. And we have an equation for it when butane, which is an alkane, reacts with halogen to form the halogen alkane. This is the name of this mechanism is free radical substitution, right? So I will just write free radical substitution here. And then for the second part, it says that they complete the reaction scheme given to show the formation of 2-chlorobutane, right? So we have the 3 steps: the initiating step, the initiation, then we have the propagation, and then we have termination, right? Initiation will always show the formation of free radicals. In propagation, one free radical will react with one molecule to give you a new free radical and a new molecule. And in termination, we will have 2 free radicals reacting to give us one new molecule, right? So this is the differentiation between initiation, propagation, and the termination steps, right? This is the difference. So now let's write the propagation step for it. We already have one propagation step written for us. Now let's write the propagation step before this. So what will happen? You will have C4H10 and this will react with a chlorine for free radical and you will get C4H9 free radical and HCl, right? Because we need to show this in continuity, right? Where did I get this C4H9 free radical from? So that's where I got it from. Now once you have this, so now these two free radicals, C4H9 and the chlorine free radical, in the termination step, these two will react, right, to give you the C4H9Cl, H9Cl, right? So this is the reaction scheme for the production of chlorobutane, right? So that's what you need to show here. And after this, it says in D, we have another question, another part which says that the rates of hydrolysis of 3 secondary halogen alkanes are compared, B, C, and D. Each halogen alkane is dissolved in ethanol and reacted with silver nitrate. So identify the order of the rates of hydrolysis of compounds B, C, and D. Right. So here, remember that this rate of hydrolysis depends on bond length, right? It does not depends on the polarity. It depends how strong your bond is, right? So the chlorine, the bromine, and the iodine, the sizes of these atoms increases from chlorine to bromine and then to iodine. So due to that increase, the bond length, which is the distance between the nucleuses of the two covalently bonded atoms, it increases, right? Because the size is increasing, the bond length increases, and due to that, the larger the atom is, the more bond length it will have, the longer the bond length will be, and the more weaker your bond will be, right? So the fastest hydrolysis would be with the weaker one, which will be iodine. So it would be option D, which would be the fastest, then it will be C, and then it will be B. And the explanation is that the rate of hydrolysis depends on the bond length, depends on the bond length, right? Bond length of the compound, right? Or the bond length of the bond, which is carbon halogen bond, right? So you need to, this would be your explanation for this. All right. Then in part E, we have a synthesis. We have some organic product, right? We are doing hydrolysis of each, right? The organic product of the product of hydrolysis of each of B, C, and D is butane to all, right? So we need to complete the table to, and the table shows some typical chemical reactions of butane to all. So if we react butane to all with potassium chromate, so first we need to see that what is calbutane to all. We know the organic product that we would get a ketone. So this means that butane to all is a secondary uh, alcohol, because primary alcohols will get oxidized to give us an acid. This is giving us a ketone. This means it is a secondary alcohol, and tertiary alcohols do not get oxidized. So the observation would be color change from orange to green, color change from orange to green. Then we have sodium. So with sodium, it shows effervescence, and the organic product would be sodium butanoate. Right now, how to make sodium butanoate? You can either draw the structure, or you can just write the product for it, the name for it. So it would be Na, right? And you can show like this, that it would be something Na or CH3, right? CO2 negative, or let's look at the iron. That I think it would be better if we just make the structure out of it. So this would be, show the structure. So this would be, so you will have O here and sodium here. So this would be your salt, right? Because alcohols have some acidity, but they only show it with very strong or very highly reactive metals. And then we have yellow precipitate here, right? And we are getting the, because this is yellow precipitates, which is of triiodomethane, and we are getting another salt here, right? So this would be I2, alkaline aqueous iodine, alkaline aqueous I2. So this would be the reagent here. Okay, then after this, it's, we have question 4 here, right? So in question 4, it says we have cyanoethanoic acid. It is a weak organic acid at room temperature. A cyanoethanoic acid undergoes an acid base reaction with NaOH. So we need to define what do we mean by the weak acid. So weak acid means an acid which partially dissociates an ion in water, partially dissociates its ions, its H plus ions or protons in water. So this is what we mean by weak acid, right? Then in part 2, it says to sketch the titration curve on figure 4.1 for the reaction of the cyanoethanoic acid with NaOH, right? So we have only one functional group, right, for the acid here. This will behave as an acid, and this will behave as the base. So at the end, the ratio is 1:1. 1 mole of NaOH will react with the say 1 mole of cyanoethanoic acid. So if we have 0.10 mole per decimeter cube and the volume is 25 centimeter cube, so this means that the titration, the end point would be reached at the same volume, because the stoichiometric ratio between them is 1:1, right? So you will start, because we have in the sketch the titration curve, so we are adding NaOH. This means we have in the burette, in the conical flask, we have the acid, right? And from the burette we are pouring down NaOH. So this means initially your pH would be closer to the acid, that would be 3, right? Not a very strong acid, that's why we are at 3. And then at 25 we will get this straight line which shows the end point, right? And then due to a high base it will reach 13, right? So at 25 this vertical line shows the end point, right? And we are at 13 because NaOH is a strong base, right, or a strong alkali, and we started from 3 because this is a weak acid. That's why we started at 3. All right, so this would be the titration curve. After that, it says write the overall ionic equation for the neutralization. So just remember the neutralization equation is H positive plus OH negative will give you H2O. Just include the sage symbols. Everything will be aqueous. H plus will be aqueous, OH negative will be aqueous, and water would be liquid. So this is the generic ionic equation for any neutralization reaction. Then it says suggest the formula of the organic product when cyanoethanoic acid is heated under reflux with NaOH, right? So when you heat it under reflux with NaOH, what will happen? You will get, this is your acid, right? And this is your base. So when you will heat it under reflux, we will get the moles, or we will get the ethanoic ion, right? So this will be CH2. This is basically oxidation, right? CNO, we will get so the if you oxidize it, right, because reflux means we are oxidizing it. So if you oxidize it using or hydrolyze it in any way, right, we will get CH2 CO2H, right, and CO2H. So we have two OH here, but because it is an acidic medium, so this would be neutralized, right? So instead of having CO2H, you will have 2CONa, right? So this would be CH2, right, CO 2Na and CO2Na, right? So this would be the product. You can write it as CH2 CO2 twice, right, and Na twice. So this would be the organic product that you will have, right? So this would be the answer to this. If you reflux it, you will get the nitrile group will be oxidized to acid, right? And now you will have two acid. If it would have been in an acidic medium, this will remain acid. But because it is in a basic medium, the base will neutralize the resulting acid. Okay, now for part B, it says that we have is very soluble in water because we are the again this is the cyanoethanoic acid. It is very soluble in water because it can form hydrogen bonds with water. So we need to show complete figure 4.2 to show one hydrogen bond between a molecule, and we need to label that hydrogen bond clearly, right? So the hydrogen bond for that we would be using OH, right? So we need to show the labeled hydrogen bond. So this would be something like this. So we have two H's and one oxygen, right? So this would be something like this, right? So you will have a lone pair from here, yeah, and this would be having a lone pair from here. So this shows your hydrogen bonds, right? After this, not with this because this is not the OH bond, only with this, right? So this would be your hydrogen bond. And then it says in figures part C that shows the synthesis of CH2CnOH, right? So you are reacting how we can get this isocyanate, how we get this ethane isocyanic acid, right? So it is formed using an halogen right? So the reaction mechanism we have it for this is it is reacting with chlorine, which is nucleophilic substitution. So what will happen first, because this is substitution, right, and the nucleophile is getting substituted, and the halogen alkane here is primary, right? It is primary here, no, it is secondary here. So secondary can go with any of the above. It can go with SN1 also and SN2 also, right? So what will happen, you will show that the bond will come here, it will be attacked from here. Yeah, this will show the electron transfer from here. This is partial positive and this is partial negative, right? However, there is nothing to show here, right? So it will come here and then this bond will be broken out. So this would be the only dipoles that you need to show, right? Also, the identify the nucleophile here. So nucleophile would be the cyanide ion, nitrile ion, Cn negative, and the mechanism is nucleophilic substitution. Right now, not need to specify which nucleophilic, which mechanism, the SN1 or the SN2. It is just clear if you just write nucleophilic substitution. Then in D, we have a synthesis again. We have a sequence of reaction starting from nitrile, and we are getting E at the end. So identify the type of reaction that occurs in step 1. So in step 1, we have the nitrile group, we have the acid group, right? So it is reacting with alcohol in presence of the acid. So what we get ester, right? So this is condensation reaction. You can also write condensation or esterification. However, esterification is usually condensation, so condensation would be a better way of explaining it. Then name HCHO, the reactant used in step O. Step 2. So step 2, it is methanol. One carbon aldehyde, that is methanol, right? Deduce the formula of E. So what would be the molecular formula? Just count the carbons. How many carbons do we have? One carbon here, one carbon here, one carbon here. So we have 1, 2, 3, 4, 5, and 2 carbons. That is 7. So we have C7, right? Now let's look at C. How many carbons do we have? One carbon here, 2, 3, 4, 5. Oh, 5 and no, this one is 5. We have 6 carbons. My bad. We have 6 carbons, and the oxygen, that if you look at one oxygen, 2 oxygen, so we have 2. And how many hydrogens do we have? So this one has no hydrogens here, this one will also have no hydrogens, this will have 2 hydrogens, two hydrogens here, this will also have no hydrogens, so it will have total of 7 hydrogens we have. So C6H7, H7, and then we have 1 nitrogen and we have 2 oxygen, O2. So this is the molecular formula. You just need to count the molecules, the atoms in the molecule. Then it says E can be polarized to form F. Draw the structure of one repeat unit of polymer F. So we have only learned the addition polymerization, and it happens between carbon to carbon double bond, right? So over here one carbon has this HH only, and the other carbon has, on one side it has CN, and on the other side it has C2H5 and O2, right? So let me just make it. So this would be C with 2 H's, right? And the other C with 1 CN, the nitrile group, and the other group would be CO2 and C2H5. CO2, C2H5. This is the compound in the displayed formula. Now for the polymer, you will just remove the double bond. Yeah, you will just remove the double bond, make it a single bond, and show continuation, that we have lots and lots of molecules, lots of monomers attached here, just like this. So this shows that we have a chain, right, which is being attached. Okay, and then in part 5 it shows we have the infrared spectrum of E. We have the different groups numbers also, right, the absorptions numbers and the different and their respective bonds. So it says, using the information given in table 4.1, identify with a cross on figure 4.5 an absorption that can be used to monitor the progress of the polymerization. So we need to select such a bond or such a peak that is present in E but not in F. So the only difference is of this carbon to carbon double bond, right? So we can monitor this, because in E you will have a double bond and in F you will not have a double bond. So we can check for this carbon to carbon double bond. It is between 1500 and 1680. So let's find this peak. This is 1000, this is 11, 12, 13, 14, 15, and 16. So this would be the peak. We will label it with a cross, right? This would be the peak which we need to monitor. So explain your answer, right? Why do we have this peak and why can we use this peak? Because E has carbon to carbon double bond, but F does not have carbon to carbon double bond, right? And the peak at 1500 till 1680 represents the peak due to carbon double bond. So we can easily, due to carbon to carbon double bond, so we can easily monitor it, and hence we can observe the progress of the reaction, right? So this was about the paper. I hope you understand it. So we meet again inshallah with a new paper. Alright, so take care. Allah Hafiz.